is yours, Ryan.
Okay. Thank you. Thanks, everybody. This is the first time I've given a talk at what is 4:40 in the morning, so I may be a little lackluster, but I assume everybody can hear me okay?
I can hear you fine.
Okay, great. So I'm talking about this today, which let me share my screen. Let's see here. One.
See either at the bottom or at the top of your screen, you should have a little box that says share screen.
Well, I practiced this, and let me go to a single screen here, one moment.
You guys have too complex setup, huh?
Yeah,
Andre with multiple cameras, you with multiple screens.
Exactly. Here we go.
Yes. Here it goes. Now it's really large. Maybe you're using a really large screen. I don't know.
Oh.
Because I see this really, and I have also multiple screens, and in all of these, it appears really large. So I just see a part of the screen.
Well, let me just do this.
Yes, that's really good.
How about that? Okay,
yes,
I can't see my notes, but that's all right. So thanks for bearing with me. So to give you a little bit of background, I'm someone who grew up with the 64. Here in the States, it was really kind of a ubiquitous computer when I was growing up in the 80s. And it was the only way really someone here with a modest income could afford to have a home computer. So it was an amazing time, and it launched my career. And so I'm still in tech, and got into the internet because I got to see that start up. And so I've spent my whole life doing tech as a result of having an accessible computer. And so that is really a big reason why I love the 64. The other thing is something about all the Commodore computers, or maybe all the computers of that generation. You really had a capability of remembering the entire memory map, or ROM calls, your pokes, even on the Amiga with Exact and Intuition, you could really remember keep everything in your head, versus something modern today where you can only really be a specialist. So anyway, in this winter during the COVID lockdowns and the pandemic, I was looking for a project, and kind of my entire life, I've enjoyed hardware. And I assume you guys can still see the screen okay? Yep, okay, great. So I was working on this, which is I have it here. So this is a bit of a detour. I was working on an 060 based single board computer, and just as sort of something fun to do. And I got to the point where I had a system that had SD-RAM. I had a system that had IDE in terms of a compact flash, serial, I2C, and I really wanted to have a frame buffer as I worked on this computer. And this project here that you see got rather hairy, is the only way I can describe it. It had a lot of programmable logic. The bus was getting complex. Obviously, the 060 is more complicated than the 6502. And I thought, here we are in lockdown. I'm stuck at home. I have my 64 out. Instead of making a frame buffer for this, why don't I make a frame buffer for the 64 and turn it into a little cartridge? So I needed, the thought was I could use a 64. I could use something like a Raspberry Pi or an Arduino, but really the 64 is the most fun. As I mentioned, you can remember I still remember things, like putting machine language programs at C1000, poking 53280, 281, 646. It's something that you remember for your entire life. And so I decided to use the 64 to reteach myself a little bit about video. So I wanted to relearn what I had known, 20 years ago about VGA and the signaling, and also really have a better understanding about how to build a piece of hardware that could put pixels on the screen. This coincided, obviously, retro's been taking off. It's very popular. My 64, even though I don't think my wife appreciates it, is in the living room, and but that's just kind of the way things are. The other thing that made it easy to do on 64 was the availability of these Xilinx chips. So Xilinx still has a line of CPLDs, which are programmable logic devices, sort of in between. You've got something like an FPGA, thousands or even millions of logical elements. You've got something like a PAL with just, dozens of logical elements. Something like a CPLD sits in the middle, and you can still do some pretty amazing things, and they're 5-volt tolerant. So they can sit on an old school bus and speak without any level shifting or any type of fancy hardware to translate between the 5-volt signals of an older computer and 3.3 or 1.8 of something modern. I also wanted this to be compatible with a VGA monitor, right? Because they're everywhere. Getting stuff that runs 15 kilohertz, we all know, is a little difficult for our Amigas and 64. So I thought, well, if I make a frame buffer, it should be something that's 31 kilohertz or higher scan rate, so you can use a modern flat panel display, which also implies you need to be pushing pixels out at about 25 megahertz rate to get a 640 by 480 screen. So this is maybe hard to see. I'll zoom in a bit, but this is what I came up with. On the left is the 64 expansion bus, so what we call the cartridge port. This port, as you know, exposes pretty much a copy of the entire 6550 or 6510, and some specific pins that give you control over the PLA configuration. In other words, the memory map. So this yellow square in the middle of the screen here is representing the Commodore 64 cartridge port. And I'm taking the full address and data bus from the 64 into the CPLD so I can work with it. The other side of the schematic is really the top half here is an SRAM to hold the video information. And then the bottom half is a very simple connection to one of these high density 15 ports that go off to a VGA monitor. You spend time with this in a PCB program, and this is what you end up with. Now with manufacturing and being able to just shoot something to China and getting it in a couple of weeks, it's kind of amazing, and it makes it affordable. This turned into a 4-layer board. The big chip, the biggest square chip there is that Xilinx CPLD I mentioned previously. The smaller rectangular chip is the SRAM. And there are other things on here. The chip needs a 3.3 volt supply, even though it will talk to 5-volt logic. So it has a small surface mount regulator, and then some pins for programming, and you got to have some LEDs to flash, right? So as one does, when it comes back from China, you populate it and you put it in your toaster oven, right? And you reflow it. This works very well. I know there's some folks, I saw just the other day, someone was complaining about I hope I'm not calling anyone out here, but someone was complaining about surface mount. Don't be afraid of it. It is so much easier and so much faster than through hole. I use it all the time. And even if you're not doing reflow, you can do drag soldering and build a surface mount board with a lot of connections, just so much faster than you can build through hole. The only trick is use lots of flux. So after you bake it, this is what you end up with. This fits the Commodore 64 standard cartridge port, with the exception of that VGA connector, that high density 15 on the right. So it pokes out a little bit from the cartridge port, or from the normal cartridge profile. But that's what you end up with after the reflow. And that's what it looks like in a 3D printed case. And that'll just slide into the back of a 64 like we're all used to with cartridges. So the final specs that I landed on, I used a standard footprint for the static RAM, or the frame buffer memory. JDEC has standard footprints for a lot of different RAMs and ROMs, and this is the standard 128K frame buffer. You don't really need all that space, but this board can be used for other purposes, like a RAM disk or whatever anybody thinks of it. So throw on 128K of SRAM. I ended up with, I put DAC, or digital analog converter, in quotation marks because it's just 1 bit per channel. So this is 1 bit per red, 1 bit per green, 1 bit per blue. So 2 to the third, 8 colors you get. There's no palette register. So these are normal kind of what we're used to in non-Commodore computers, chunky pixels, and no redirection going on for palette lookup or anything like that. As I was making this, I did take a few detours into trying out using, I made 2 other versions of the board. One used cascadable counters to just iterate through the SRAM memory to get the pixels on the screen. I ended up not liking that because it added complexity. And also, I would like to expand this to maybe have something like a pointer or a sprite. And that would, since you can't have random access with a counter, that got rid of that. I also did a version of this with a dual port SRAM. So an SRAM that has, you can access it from almost 2 different buses on either side. But those chips are very expensive. So that was, I dumped that as well. So here's how it works. There's a state machine. So there's logic inside that CPLD that reads a byte from static RAM. Every 8 pixels, or every bit in that RAM, that gets shifted out to the screen at a 25 megahertz rate, unless you're in a multicolor mode, which I'll explain in a moment. So here you see sort of the logic. So in a monochrome mode, and we're not in a blanking area of the screen, we're just setting all the DAC colors, or all the DAC outputs, to 1s or 0s. So you're either getting a white pixel or a black pixel when you're in a monochrome mode. So that's 1 bit of memory equals 1 pixel on the screen, and it's linear. Okay. This gives you a 25 megahertz pixel clock. It turns out that VGA for 640 by 480 is actually 25.175 megahertz. That's less than 1%, and it's close enough, works great. I think lots of people do this. I haven't found a monitor that doesn't sync to it. So it worked. 25 megahertz versus 25.1 makes absolutely no difference. If you're selected a multicolor mode and we're not in a blanking space, the logic says we want colored pixels on the screen. So this, I think, is somewhat novel. It's a little difficult to explain, so I tried to make a diagram here. So what I did was, if you're familiar with a Bayer matrix on a camera, like on a digital camera that has green pixels and red pixels and blue pixels, that's sort of what I did here. Because I have limited resources in that CPLD, I can't really do lots of, I can't be fetching enough bytes per screen or bytes per second really to throw out like something like a full color image, right? I just don't have the capability for all those counters. I would fill up the chip. So what I did was, knowing that humans perceive spatial information toward the middle of the spectrum more so than towards the edge of the spectrum, I made the green channel half the resolution of the monochrome screen, and I made the red and blue channels 1/4 of the resolution of the monochrome screen. So each pixel, when you're in monochrome mode, you're either losing half the resolution, or when you're in multicolor mode, you're either losing half the resolution for the green channel or 4 times the resolution for the red and blue channel to make up that pixel. So it's sort of it's only horizontal that this takes place. So you still have the whole 480 vertical resolution, but this changes your per line. I also thought about doing something like a ham mode or some type of delta from pixel to pixel, but this turned out to actually work pretty well. And because we're more sensitive to green, it seems to work pretty well. So to make if you need to make a multicolor picture or you don't understand what I just said and I explained it poorly, on my Git, I do have a Python example that encodes multicolor information. So you can use something like image magic to pull out your red, green, blue channels, run it through this Python script to get a compatible binary to display on the frame buffer in multicolor mode. So anyway, so over Christmas, I made this hardware. I got the board back, I baked it. That's all great, but then you have to actually make the board work. So that's when you get into both the software side and programming the CPLD. So I moved on to that. On that board that you saw earlier, I actually did not pre-place any of the pins besides power and ground and reset and the main clock. I just fed those into the chip where it made logical sense on the board. So with one of these CPLDs, you have a connection matrix around the outside of it that allows you to, hey, route this pin to this resource inside the chip. So really, you can put the chip on the board before you know exactly what pin's going to be doing what. You then build what's called a constraint file from that schematic to describe to the software saying, hey, my red channel is going to be on pin 68. And so whatever you come up with for logic, I need that red pixel to come out of this certain pin to get to the VGA connector. Then you use what's called a hardware description language to build a configuration file to program that CPLD. So just like you were talking about programming a ROM, this is a very similar experience, except you're using a JTAG port and you're burning it to the CPLD and it's flash. This is a contrast to an FPGA where you usually have an off-board static or an off-board flash chip on a serial interface that boots it up. So this comes up, the instant 64 comes up, and it's non-volatile. If you're not familiar with these hardware description languages, they're strange. It could be a little bit hard to wrap your head around, and it's something though to try because it's very interesting. It looks a bit like C. In this case, I used Verilog. It's like C, it looks like C, except that every single line of code really is executing at the same time. What you're doing is writing code that's going to be synthesized into bits that tell that CPLD how to interconnect resources on that chip. So what you can do is build both just simple formula or combinational logic to describe things like Boolean operations for inputs and outputs, and then also use the clocks that are driving the chip to make sequential logic to do things like that pixel pipeline where we have a state machine that's slowly shifting out quickly shifting out pixels to the screen. It also has a little bit of RAM in the form of flip-flops and some buffers to make read-write registers. This whole process is very test or simulation oriented. And I want to call out, there's a gentleman, I forget his name, working on a replacement for the VIC-2 right now, who it's just an amazing set of videos, and you'll find it if you search for VIC-2 replacement on YouTube. And you can see this is a very test-driven or simulation-driven process where you are encouraged to write a test fixture to describe how you want your circuit to act before you actually describe the circuit. And that sort of mirrors modern software development, right? Where you write some type of test perhaps before you actually write the code, because the test is easier to write and easier to describe the behavior. So the same thing is true here. This is what it looks like, just to give folks a taste. The top half with those assign commands are the Boolean or combinational operations to say, hey, output a red pixel when we're in the visible range of the screen. So meaning when I'm in the blanking as the raster's off the screen or off the bottom of the screen and returning to the top, we don't want pixels on the screen. It needs to be blank. So that's what those assign statements do. Though all those statements are executed at the same time, they are not driven by a clock or anything else. So a little bit different than an old procedural programming language, right? Where you're going from top to bottom. And then for things that you need to be procedural, like a state machine, here's a small example of what we're doing every 100 megahertz clock on the board. So all the clocks are derived from a 100 megahertz oscillator on the cartridge. And there's two blocks here. One you can see is for reset, and one is for when we're not in reset. So when we're not in reset, a reset is high. So that about the middle of the screen there, you can see, yeah, I have a pointer. This section here is very simple. I think it's a good example. So we're incrementing a divider. We're transferring any registers that we need to, and we're also loading any data from SRAM that we need to. And this also controls this tri-state buffer to get on and off the 64 bus. So the 6510 can have the bus, but you have to build these constructs inside these always sections that are driven by the sensitivity, in this case, the clock changing, and then you tell it what you'd like to do. So there are some open source or free as in beer tools called GHDL and Icarus Verilog, which compile and run on everything. If you want to try some of this stuff out, all my code is out on my webpage and linked to on GitHub. So you can look at this, but it's a very interesting thing to learn if you don't get exposed too much to hardware, but you want to play around with hardware. Something like the Mr. FPGA, which was mentioned earlier, uses, it has probably a million lines for some of these things that are describing, or something like the Vampire, right, is using tons and tons of Verilog or VHDL, some type of hardware description language to describe these computers we love in a software form. Here I'm using it to make a little video card. So it was several hundred lines to make a VGA card. And you take this, you compile it, it looks for errors, and then you run it through what's called synthesis, and it makes a bit stream which you program in to the chip. So you have the hardware now, it's working. How do you talk to it from the 64? There are two different versions of the bit streams or flash information for the cartridge. One uses registers in DE100, so DE00, which is a common, it's IO1 on the 64. And one uses a window of 8K at 8000. I prefer the register-based approach. I thought I'd really like the window, but you lose 8K of RAM, which you can't really afford to do on a 64K system when you're working with big images. So the one I often use is the register-based approach. And there are 4 registers, a pointer for low and high byte, what operation you want to do, and then what type of data you want to operate with. And as soon as you touch that operand, you make a write to it, then the cartridge interprets it from the registers. So here's an example in 6502 assembly. You can do this in BASIC as well. So when I was bringing this board up, the first time I used it in BASIC just because it's easier since the machine boots up in BASIC, right? So here you can see my registers are laid out in DE1000 or DE100. I'm using a couple 0-page registers to quickly iterate. And then here's some code that just, one of the first pieces of code I ran to run on the frame buffer. So like the first few lines there, I'm clearing out a couple of spaces in 0-page. I'm using 170 decimal, which is just a nice 101010 pattern. And then I'm going through and writing 64K of it in this loop to the frame buffer registers. So I get a 640 by 480 monochrome screen with vertical every pixel on and off. And this worked. So this is how you talk to it. And again, this code is all online. This is what it looked like in my living room over Christmas. The programmer for programming the bit streams on the right on the Windows laptop. You see my 64, you see the cartridge in the back of the 64. On my big monitor there, it's split screen. I have the Commodore output running BASIC from the composite output of the 64. And then I have the my frame buffer output. And this is what an off by one error looks like on your own hardware. So I did a loop, and you can see those lines should be vertical, and they're not. They're off by one. And so a small change between 640 and 639, and I was in business. So this is my first image I put on the screen, just a monochrome image. Again, this is a machine language program or a Swiss language program that's out there you guys can check out. And that's showing off monochrome mode. Oh, this was actually my first multicolor image, those small red, green, blue lines there, you see. And then I did a Julia set. Not the prettiest thing in the world, but you know, it was a second screen on the 64. I was pretty happy with it. I learned a lot about video and operating with the 6502 bus, and had refreshed a lot of my knowledge about these things. So a couple problems I ran into. One, you can do a lot with the hardware description language and even now PCB design with open source tools. In most cases, you cannot make the bit stream with open source tools. You have to use the first party tools from a manufacturer. So in this case, Xilinx, you use an old version of the tool, and it's not great. It's crashy. You have to use a very specific version. I used version 10. If you're trying to do this and you have problems, feel free to reach out. It's kind of awful, some of these tools. They're gigantic, monolithic apps, and they're hard to deal with. There are some folks working on certainly open source bit streams for some of the simpler FPGAs, and I would imagine they'll get to some of these CPLDs because they're just so popular for retro uses. So that would be really great, because I have no doubt that they will do a better job than the OEMs when it comes to working with the software. The other thing I ran into, I picked up a Ultimate 64, which is another really amazing piece of hardware. And I wanted to use my cartridge in that, and I put it in, and my cartridge got really hot. And I thought, wow, this is bizarre. I thought I had broken the cartridge. I went back to my normal 64C, worked fine there. I hadn't cooked it. It turns out that the Ultimate 64, at least I haven't tried the latest firmware for that, but it turns out that you actually see logic levels on the cartridge port before there's power on the cartridge port. And that's a big no-no with a CPLD. It latches up inputs and outputs. I don't think it gets configured correctly, and it just sits there and cooks. So the cartridge does not work on the Ultimate 64. I did exchange some email with Gideon and the maker of the Ultimate 64, and it may work in the newer versions. I'm not super likely to try it, even though it would be really cool to be able to push pixels around at whatever the thing runs at now, 20 or 40 megahertz, which is insane. I just don't want to fry my little board and have to make another one. But you know, maybe I'll try it. So if you make this, don't use it in the Ultimate 64. So some other things I might want to do with this in the future. That little CPLD in here is absolutely packed. The resources in here that you're referencing with that description language, or that you're synthesizing into with Verilog, there's 144 of them, which is actually quite a bit compared to something like a PAL or GAL. For what you're seeing with the high res and low res modes, and either register based or banking, a window-based approach, you're using up all the macro cells for all practical purposes. So there's no more room for things like a sprite or anything else. There is a larger CPLD that has a slightly different footprint called a 288. So I would almost double the resources there. That could be interesting. I might do that if there's interest. There are also, if I went to something bigger, maybe I could get a pointer in. And I think that would be pretty interesting to have a high-res screen with at least one sprite. Something like scroll registers. We're familiar with the scroll registers on the 64 and Amiga, how you can go, 8 bits shifted left or right and up and down before you have to copy the screen. That could be done very easily. Something like a copper list or display list could be done. I do need to write a better demo for this. So I've got in my code online, I also have a video on YouTube. There are 3 or so multicolored demos in my one monochrome demo. I need to write something with some animation like fireworks or something, and I just haven't had time. Or if I went all the way to an FPGA and did do level shifters, I could do all these things, right? But at that point, you're really probably losing the spirit of an 8-bit computer. And I'll save that for the, I'll save that for my 68060 board that I'm working on. So I have one question for the team. One thing I found for the crew here, one thing I found was, so the 6510, the spec says everything should be valid on the rising edge of the phase 2 clock. And what I really found was that signals were valid on the negative edge of the phase 2 clock. And I don't know if that's anything that anyone else ran into, but that would be interesting to hear about. And then if you folks have any questions, I'm happy to take any questions or go deeper in any particular topics. But certainly thanks, Sebastian, for the invite. And this is pretty fun, except for the getting up at 4 o'clock part.
You're welcome. You're more than welcome. I see one question came up, but it has been answered already. So it was, are you using ceilings? And so the answer was.
I have one comment, maybe. So is my audio working now?
Yes, perfect.
It is.
I'm,
yes.
Dialed in by phone. Anyway, yeah, I think the issue with the signals valid on the falling edge is because on the falling edge that's the one transition of the 6502, but not being ready on the rising edge is because I think of the C64 splitting the bus between the BIC and the processor. So while Phi2 is the clock is low, the video chip is using the bus, so you don't see the thing. That's actually the reason why the 6522 VIA doesn't work on the 64 without any problems, because you have to delay the rising edge of the clock for that.
Ah, wow, fantastic! I got a question answered. Thank you. That makes a lot of sense, because so the 6502 is probably data valid on rising edge, but the VIC is in there then. And then we're waiting for falling edge before we can have, before we should consider anything. So that makes all the sense in the world. Thank you.
You're welcome.
That's also the benefits of these meetings here, right? Is that people get to talk to each other as well. Sometimes that saves you some Googling or research or whatever. I had actually a question as well. You said the code is online, but then I guess that's on the website that you're posting there. You mentioned your YouTube channel. Is there a link from your page there as well to the YouTube channel?
There is, and I will say I'm not a YouTuber. You can tell I'm terrible at video, but I do have about a 8-minute video demonstrating which is linked to from the page. So if you want to see an actual demo, which I'm not set up to take in composite and get it into a Zoom, go to watch the video, and you can see me actually interacting with the frame buffer.
Perfect. I don't know if there are other questions. I see a comment from Casper about the Ultimate 64 that had also problem supporting the Turbo Chameleon 64, but it could be the same issue. I don't know if there is any follow-up discussion on that. If no more questions, or maybe if additional questions are coming, please post them in the chat. Ryan, really a big thank you for joining. and you're of course welcome to stay a bit to see if there are
Yeah.
any questions coming back. Thanks a lot. And I guess looking at the time we have, we are completely out of schedule. But